B was asking for the Maclaurin series of an integral. Sorry, this is going to be split up in so many videos. I keep leaving my video to check the original problems, like what they say, so I actually know what I'm talking about. But this one is for the integral from 0 to x of e to the t squared, almost exactly the same thing as before. It's just e to the x squared versus e to the t squared dt at x equals 2. It asks for the Maclaurin series of this, so I was a little confused and I solved it as a Maclaurin series. To be centered at x equals 2 would be a Tyler series, so I didn't know if it was like a trick question, or what I did is I used it as x equals 2 for my integration later. But finding the integral of this, or to find the sum of this, you turn it into a series because a series can estimate it. So you get for the integral of e to the t squared dt, you get the integral from 0 to x of the series n equals 0 to infinity of t to the 2n over n to factorial. That's another reason why I got this, because it was going to be useful here. dt. This is equal to this. This is equal to this because I took the integral of it. That's why it's moved to the right. Had to remember for a second, look at my work. And then this is where I wrote in that x equals 2 to make it easier. I don't know if I was supposed to do it a different way, but I did choose the easier option. So then I write out the Tyler series. You get t plus t cubed over 2 plus t to the 5th over 8 plus t to the 7th over 36. And you keep plugging them in forever. I think I went 7 terms for this to find the final estimation. And then you add them all up and they equal about 20 after 7 terms. And these weren't notes for me. This is at n equals 0, n equals 1, n equals 2, n equals 3, and then it would have been so on if I added more terms. So the answer to B is roughly 20, or about 20, or estimated 20, because I only did 7 terms. If I wanted to like be really sure, I'd have to do like an infinite amount of terms to know it's 20. Pretty sure anyway. Last question asks fx equals 3, or last question states that f of x equals 3e to the negative x over 6 for all of x. The function h satisfies hx equals k to the derivative of f ax for all of x, where a and k are consistent. Maclaurin series equals 1 plus x. This is the one provided. The Maclaurin series provided is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth, following that pattern until you get to xn over n factorial. Find the values of a and k. So the first step was to find the derivative of f, which is negative 0.5e to the negative x over 6. I wrote 0.5 because I thought it'd be more space effective than a 1/2, because I don't like cramping my fractions, but I still do it a lot. And then h of x just equals what was said before. So that's not new, but then we plug in our value for the derivative of f that we found. So now it's k times all of that. And in the top, worth noting is instead of negative x over 6, it's negative ax over 6. Forgot the a at first, that's why it's tiny. And then it equals negative 0.5k e to the, it's just multiplying the k in. Then you go down here for the Maclaurin. Based off that pattern, you can see that it's just e to the u. That's the basic pattern that any e to the u uses, meaning that u, in this case, equals the negative ax over 6. That's e prime. U equals 1. 1 equaling those there is the answer. I don't know why I'm saying this so weird, but when you multiply by 6 and assume that x is 1, you get a equals -6. Then plugging in your -6 before, you get 6 divided by 6 canceling out, which is -0.5k e to the x. X equals 0. You get -0.5k times 1 equals 1. -0.5k times 1 equals 1. So to find k, you have to multiply by -2. And then you find, you just multiply k equals -2, a equals -6. Sorry for sounding flustered explaining all this, but I'm not a teacher and I'm bad at it.